Well, all right, now you're all set up. Let's get started. So we were in module 5. Module 5 was on the topic of bending for beams, basically. You became familiar with the concept of distributed loads. You solved some problem in your assignment 3, and you should now have a good idea what is a distributed load and how you can solve the problem with a distributed load. Our next topic, which is the today lecture, is on the internal reaction for a beam. What are the internal reaction for a beam? Let's say you have a beam like this one that I showed here, and you have a general load. By a general load, I mean what I showed here. Let's say this load, we call it W, and because this W is not constant, it's changing. It's a function, and this W is equal to any function, let's say fx. But in this course, typically we just study the distributed loads that either they are constant, like a rectangular shape, and the linear load, which is more like a triangular shape. All right. So this fx is a simple version. So as a result of these distributed loads, these beams tends to basically bend. But before that, let's say if I slice this beam to lots of slices like the one that I showed here, and on one, let's say one of these slices, let's say here, if I look closely, maybe there is one portion of that distributed load on this small slice, right? And imagine that this beam is made out of all these slices being glued together. Now, if I try to draw the free body diagrams for just one of these slices, let's say this is a small one here. So it's going to look like something like this, probably. I'm just drawing it bigger a little bit, right? So this force, try to basically slide it off the rest of the beam. You can sort of imagine like that. But because we glue all these slices together, right? Remember I said, imagine this beam made out of lots of slices that we glue them together. Now there's going to be friction on each side of these small element or a small slice here to prevent these things coming off. This shearing force, this friction force, we call it a shearing force. Shearing force. And we use the notation V basically to show shearing force. Why V? Well, you can Google it later. There are a lot of discussion, but early people who decide to use V because they thought this shearing force is more like a volume things. It's on a cross section, but it's a complicated things. Don't think about it. So some people in the past, they decide to call it V, to show V for shearing force. But it's important to know where it comes from, right? And it's very simple. Always imagine this beam as lots of slices like this one. Each load on each slice, try to basically slide off this small element off the rest of beam, but there is going to be friction between them. Remember the shearing stress that I explained to you? When two things want to slide on top of each other, there is going to be a shearing between them, and we call it shearing force. So therefore, we know that on each cross section of this beam, no matter where I look at, there's going to be a shearing force, which we call it V. What about bending moment? Okay, so we all agree that because of this load, and also we are in mechanics of material and things are flexible, this beam probably, and let me exaggerate, tends to sort of sag and deform to something like this. All right. So if the beams deform to something like this one, what's going to happen? on the, let me show you maybe a better picture. So on the top of this beam, you can imagine the beam is going to experience compression, and on the bottom, it's going to experience tension. So in other words, here is going to be compression, and on the top is going to be tension. Let me show it here, maybe. Okay. Let's say this is the beam, a beam that I have, and it's very flexible, okay, a beam. And let's say I have lots of loads on top of this one, right? And as a result, this beam is gonna deform, and I'm just exaggerating. And now you all agree that if I deform this one like that one, the layer at the bottom is gonna be under tension, right? See these things, when I do that, it's going to be under tension, but the layer at the top is going to be under compression. Even over here, maybe it's difficult to see. There are some wrinkles here on the top here, which try to compress everything, right? And if I exaggerate, something like that. The outer layer tends to becomes bigger, right? Stretch, and the inner layer try to compress and becomes sort of smaller, right? So when I'm bending it, then the bottom layer is under tension, the top layer is under compression, and opposite, the same. If I bend it like that one, the top layer is going to be under tension, the bottom is going to be under compression. So the beam that I showed you, hopefully you saw that one, right? This beam, okay, I bend it. And now I said, imagine we cut that beam and we're just looking at the section of that beam. All right, this is a section of that beam. And the same things, we try to bend it, all right, that's a small section. The bottom is under tension and the top is under compression. Now, if I look at the cross section of this beam, let's say this is the cross section of that beam, all the points here, right, I put this dot there, all the points here at the bottom, they are going to be under tension. Remember, this is under tension. I will bend it like that. The bottom is under tension, and all the point at the top, they are going to be under compression. So if I look at the 2D view of this one, then this point is going to be under tension, right? We show it like that one, and this point here is going to be under compression. Do you all agree? If somebody disagree, say it now before we go further, okay? Because this is important to understand what's happening here. Again, one more time, this is a section of that beam, which we try to bend it like that one, all right? And we all agree that the bottom layer, this is a layer, it's under tension, the top layer is under compression, and this is a 2D view, okay? If I move from top to bottom, right? So it is under compression. Then we agree that the next layer after the top layer is also under compression, but maybe less compression because there is the top layer protecting it, right? So it's going to be compression like that one. And the same for the bottom one. So it's going to be under tension, but maybe a little smaller because that's the second layer. And so on. So we are compression here and we have tension here. Probably somewhere in the middle, things are going to change. By change, I mean the tension, the compression is going to turn to become all of a sudden a tension. So it becomes smaller, and now they become tension. All right, something like that. Maybe not a good drawing, but something like that. So in other words, when we have a beam, a portion of the beam is going to be under compression, a portion is going to be under tension. So these loads is more like a distributed loads. For these distributed loads, I can find the equivalent, right? Remember, always we said, let me draw a cleaner picture now here. So then you could follow what do I mean exactly. All right. So let's see these loads that here that we have, distributed loads. Remember, we said we can change them to a concentrated load by finding the equivalent, which is going to be something like that here, right? And this one, a tension like that. So these two loads, okay, these are the equivalent of this distributed load on a cross section. So we have a compression here and we have a tension here. Because of symmetric, these two are equal. We have two parallel loads. They are equal in magnitude and they are in opposite direction. We learned before that these two loads can create something which we call it a couple, or in other words, a moment. All right. So let's go back to my note. I know this portion of the lecture is a bit boring, but it's important to understand it before we go further. All right. So let me draw it here. Going back here. So as I said, we draw a section of this beam, and over here, I'm just drawing it bigger so you could see what's happening. Okay. And this portion, again, we said because of the load, it's going to bend like that one. And this bending create on each cross section, let's say something like that one, which I showed you on a cross section, is going to create some compression here and some tension here, right? Which we said as a result, we can show that on a cross section by basically a moment, M. This M, we call it bending moment because it tried to bend the beam. Where it comes from this transverse load. And by the way, the transverse loading, it means the loading that they apply across a beam, right? They apply across a beam. They are unlike an axial load, like this one is an axial load. This is an axial load, while this guy is a transverse load, okay? Here we don't have any axial load. There is no axial load, but this transverse load results in some internal, as you can see, axial load, all right? Which we saw this axial load, it comes from when we try to bend the beam. And the result of this internal axial load is something, creates a bending, which we call it a bending moment. Our job in this chapter is to find this M and V. So in other words, if you convince now, at any cross section of this beam, no matter where I'm looking, if I cut this beam at any section, all right, and look at that section, all the molecule and all the elements on that section, they are under a bending moment M and shearing force V. And this M and V, they comes from this W, these distributed loads, all right? Or this transverse loading on the beam. And our task in this chapter is finding these M and V. So before I go further, is there any question on this part? Okay, if there is no question, let's move on. Okay, with that introduction, let's now get to the actual part of this topic or this chapter. So as I said, our objective here is to find these V and M, and from now on, by V we mean shearing force and M bending moment. Also, we want to draw this V and M because this V and M, probably they are not going to be constant. So if I look at the cross section of this beam here, probably I'm gonna see one V and M. If I cross section over here, maybe because the loads are larger, I'm gonna see a different V and M, right? So another objective that we have, we like to see how this V and M change. And to see how this V and M change, we like to draw two diagrams, which they are known as V and M diagram, or shearing force and bending moment diagram. And let's say for this beam, and I'm randomly drawing something, like just made up something. Maybe the graph looks like something like that. We don't know. Maybe draw it better. It's not going to be that complicated. Maybe something like that, or something similar. This is V, and this is M, and maybe M is going to change something like that. So, and they are function of X, all right? So our task is then finding these Vx and Mx. We want to find out this function, Vx, and this function, which is Mx, and draw them. Why we need to draw them? Because we are interested to find out the maximum values, our third objectives here, the maximum values of V and M. We like to know, for example, after looking at this graph, we may realize that, well, maybe the maximum shearing is, let's say on this graph, I draw something like that. It is happening over here. That's the maximum V. And here is the maximum M. So this is V max, and this is M max. We need to find these M max and V max because at these points, they are critical points for this beam. The beam is going to break. And if we want to design a beam, we need to base our design according to these numbers, M max and V max. So it is critical to find these values. And also it is important to know where this maximum happens, because we need to know where, if this beam is going to break, where it's going to break. So maybe later we can reinforce that area with something like adding extra plates, welding extra plate, or if it is wood, gluing more wood to it and make it stronger around those areas. Okay, this is our objective in this topic. And again, as I sent an email yesterday, this is an important topic. In future, you're going to see the distributed load and how to find this M and V a lot. Maybe not for a beam, even if you are in bio mechanic and biomed, still you're going to use this concept of distributed loads, maybe on a bone or on something. I have example to show you later, which you need to understand this concept. So when we talk about beam, it's not going to always be a bridge or a construction. It can be a part of a body. It can be in mining, for students in mining, it's going to be, let's say, a tool in mining. And in material, the same. And also for other students, it's going to, you can find application. All right. All right. So this is our objective then. Finding V and M in each cross section, in different cross at different points of a beam, different cross section of a point of for a beam. Draw the V and M and finding the maximum V and M. Okay. Is it clear? If there is a question, please ask now before we go further. Okay, hope it's clear. So now let's get to the math. As I said, if we cut a beam, if we cross a beam at the cross section, it's going to be a V and M. So we decide for a convention. By convention, we decide something, and all of us are going to follow that convention. And this is going to be our convention. So maybe if you open a different book, they decide for a different convention. But that's the most common convention that most of textbooks use it. Maybe there is some unusual book that uses different things. So this according to this convention, we say if we cut a beam to like somewhere at any point, if we look at the left section or the right section of the beam, this is how we decide to show V and M. Like on the left, V is going down and M is positive, is counterclockwise. On the right is the reaction of these loads. So exactly the same loads, but different direction, all right? Again, this is just a convention. It doesn't mean when I'm crossing, looking at the cross section of a beam, always on the left, V is gonna come down. No, maybe after I do the calculation, you will see that V may turn out to be a negative number, which is fine. Negative means that the direction that we picked is wrong. The direction is in the opposite direction. But to be consistent, we follow these like rules, okay? Let me show you in this example, so it makes more clear. So we have a beam, and the question in this example, we want to draw the free body diagram, like the FBD, when we cross this beam at C, at point C, all right? So let me say that because of this load that I have, I know this beam is gonna have two reactions, right? This one and this one. That's we know. And now we section the beam at CC. So now I draw the beam to two sections, like section over here. And the section over here on the right. Okay, the same beam, the same things. Maybe let's call them A, X, A, Y. And this is only one reaction, B. And the same things is going to be on these. Nothing is going to change because I just caught at C. So here I have B, I have AX, and here AY. So I have a distributed load, and we know when we see a distributed load, we just find its equivalent because it's easier to work with, right? So this is the distributed load, and the equivalent of this distributed load is going to be a big load here. And we know that if this load, let's say the intensity is Q or W, then it's going to be Q multiplied by L, right? L is the length of these things. So far, this is all external loads, okay? Exactly as we see things, the external loads, we put them there, except for the distributed loads, which we put the equivalent. Now, when I'm sectioning this portion, we know at this cross section, something is going on here, like something is going on here, which we discussed it, right? We said it's going to be a V and M at any cross section. Those V and M, the way that we show them is going to be, okay, let me go there. So on the left side, this is V. On the right side, this is V. Okay. And for M, this is going to be M, and this is going to be M. Okay, this is V, C, M, C. I just use the C and the C here to show that this is the V and M for this cross section. And similarly, VC, MC, and VC. Okay, these numbers are exactly the same. And these are going to be our free body diagram. And because everything is balanced, everything is in equilibrium, no matter if we solve the left free body diagram or the right free body diagram. Okay. Both of them are going to give us the same numbers, the same VC and MC, because these VC and MC, they are just the action and reaction on this cross section. So this is important to understand how to draw the free body diagram when you cross a beam. And please ask me a question if you cannot follow here, because that's like the most critical point of like this topic. If you can draw a free body diagram, the rest is just, you're going to see is like previous. You just use the equilibrium equation and solve the problem. It's just a matter of drawing a right free body diagram. Okay. Is there any question? No? Okay. If no, then let's solve one example together. This is the easiest and simplest example in this topic, okay? But if you can understand and follow this example and each step, you can solve any complex and complicated problem. So then let's do it together. And in each step, if you cannot follow, please unmute yourself and ask. So I have a beam. There is a load 10 kilonewton in the middle, somewhere in the middle, not exactly middle, at point B. And the question is asking us to find V and M, the internal reaction for this. Our first step, always with beam, is to find the reaction at the supports. That's easy. All of us, we know how to do it. We just use the equilibrium equation, and here we find them. I assume you know how to do that. So let's say we find this one, it's 6, and this one is going to be 4 kilonewton. Okay, that's the first step. Then we divide this beam to different regions. What do I mean by region? Well, we start from the left side always. And we draw a line like that one. Yeah, we start from left. And the reason we start from left, because we're going to have our x-axis always starting from this datum over here. So like something like that. And we usually call it x. All right. So we start from left, and then we say, okay, the next boundary after the first one, which is at the very beginning, is going to be this line. Where we put the boundaries, remember, when you start from left, whenever there is a change, then you have to put a boundary. From point A to B, everything is the same. There is no difference between this point at the beginning or toward the end, right? But here I have a boundary because there is something changing. Then from B to C, nothing is going on, so I put my second boundary here. So I divided this beam to two regions. Let's call them 1 and 2, right? So later when we refer to them, we know which section we are talking. And then the next step is I just cross the beam for region 1, somewhere in the middle. Not exactly in the middle, somewhere there. We don't care because we say the parameter x, right? X means can be any number. It can be 1 meter, 2 meter, 3 meters, as long as it is between A and B. So I cut the beam at this point, 1, and now I need to draw the free body diagram for the left or right. Remember, left or right. We don't have to draw both because we said they are exactly gives us the same values. So this is my section on the left, and then I draw the free body diagram. Free body diagram, so the external loads, that's exactly what we can see. It is 6 kilonewton here. And then because we are looking at the left section, remember left section, we are going to have V coming down and M is like that. So it's going to be then V1 and M1. This is my free body diagram. And what is the distance from this point, let's say A, right? This is point A to this point, let's call it C1. We call it C1 because it is or S1, section 1, whatever you're comfortable to call it, like S1. The distance is x. So now that I have the free body diagram, I write down my equation here at the top here. I write down sum of the moment about S1 is equal to 0. Because remember, it is in static, everything is in equilibrium. We take the moment about point S1, which is this point. So we have M1, which is positive. It is counterclockwise. Then we have -6 multiplied by the distance, which is x, equal to 0. From here, I get M1, which is 6x. And then the second equation I need to use is sum of the forces in y must be 0. So in y, I have 6, which is positive, going up. And then I have minus v1 going down. From here, I get v1, which is equal to 6. So this is the equation for bending, and this is the equation for shearing in this section. And this section is between A to B. This is for section 1. So we'd better write at the beginning, section 1, which is valid for x's bigger than 0 and less than 4 meters, right? It is important to write at the beginning, so later when somebody is reading your solution, they understand this equation belongs to which portion. All right? So very, very simple so far. And we need to do this similar things for section 2. We section it somewhere here, okay? And we draw the free body diagram. Because this is the first example, let's try both left and right. So, and see what happens. So free body diagram, this is my section, right? And again, remember this distance is x, somewhere in the middle, not exactly middle, somewhere there. So in other words, this is like this distance is x. Okay, that's the same x as before. Because when we say x, it's a parameter. It doesn't matter if it is 3 meter, 4 meter, 6 meter, and so on. So let's see what we have here. We have the, like this load 6 here. Also, we notice that we have this 10 here, exactly over there. So that's 10. And then we have the internal loads. Again, because we are looking at the left side, we have the V and we have the M. This time, let's call them M2 and V2. See the free body diagram, exactly as I see. Whatever I see here, the external loads I draw, and this section, same. So now let's do the same things here. This is for section 2. Which section 2 is valid between x's bigger than 4 and less than 10 meters, right? Section 2 starts from B to C, which is from 4 meters to 10 meters, not 6. Don't confuse that, right? It's 10. Remember, x starts at the very, very beginning. So at point C, x is 10. So that's section 2. We write the equation, sum of the moment about, okay, this point, let's call this point that we section it, let's call it S2. About point S2 equal to 0. Let's see what we have. We have M2, which is positive, right? This V, by the way, doesn't create any moment because it's passing that point, right? It's crossing that point. The distance is 0. Then we have this 6 multiplied by x, and it is negative 6 multiplied by x. And then we have this 10. It is counterclockwise, so it is 10. Remember, we are taking moment about S2. This 10 try to rotate everything's counterclockwise, about point S2, right? It's more like, imagine you are with your car and you're driving around the roundabout, okay? So you're rotating in a counterclockwise direction. All right, let me get rid of that. So, and what's the distance? Well, from here it's 4 meters. The whole thing is x, so it means this distance is then x minus 4 and equal to 0. We simplify this equation, m2 give me minus 4x plus 40. Okay, that's m2. And the second equation always is sum of the forces in y equal to 0. In y, what do we have? We have 6 going up, minus 10 coming down, minus v2 coming down, equal to 0. And from here, I can find v2, which is minus 4. Here is my shearing force and bending moment for section 2. Which section 2 is valid for x's between 4 to 10. Okay. So just for this example, we don't need to do that. What if somebody pick the left, draw the left diagram, right? When that person section 2, he or she realizes that the section 2, it's better to use the right side. Let's try that one and see if we get the same answer. Okay, the free body diagrams here, this is the load that we have, and it is 4. We don't have anything else. So the section that we have here, V is going to be like that, and M is going to be like that. So this is V2 and this is M2. Don't forget, on the right side, right, V is going up and M is clockwise. They are like the opposite direction of the left side because they are action and reactions, right? So using, okay, method number 2, using right side free body diagram, like this one. So this point again is the same point, S2 or S prime 2, doesn't matter. You want to call it S prime 2, that's fine. Sum of the moment about S prime 2 is equal to 0. So what do we have? We have M2, which is negative because it is clockwise. This V do nothing, and then we have 4, which create a moment, right, about S, which is positive 4. And now somebody tell me what is the distance between this 4 and this S prime 2? Because we are taking moment of this 4 about this S prime 2. What is the distance? Like I'm asking this distance, right? We need to find out this distance because we are taking moment. Any idea what is this distance?
10 minus x.
Exactly. Thanks, Sajida. So the whole thing is 10 from the beginning to here is x. So this distance has to be 10 minus x. So 10 minus x equal to 0. And simply we find m2 minus 4x plus 40. So you realize that we got the same equation that we got previously, all right? M2, M2. So let's try it for this Fy, sum of the forces in y direction equal to 0. And it gives me what on this free body diagram? I have 4 going up. I have V2 going also up, nothing else, equal to 0. V2 minus 4. Exactly the same things. Magic, right? these two are totally different, like the free body diagram on the right and on the left, they are totally different, but we got the same things. Now, it's not magic, right? It's because it's in a static, everything is in equilibrium. No matter which view we are looking at a section of a beam, they are just action and reactions. And based on this convention that we used, we get the same equation. So in future, you don't have to draw the free body diagram for both sides. It was just an example to show you. Just pick the simple portion. Like in this example, if I want to solve it, I don't use the second section that we did here, like the one that it is 10, because it has a lot of loads on it, right? It's more complicated. I just use the right side, which is easier. Okay, so far, is there any question? Okay, it's silent. So I take it as that is clear. All right, so we found what the question asked us. The question asked us to find this V and M, and we are telling that this V and M, they are like, they have formula. They are not just a number. V is just a number. V for section 1 is 6, all the way from A to B, no matter where you cross the beam. V1 is 6. It means, and the unit, by the way, this one is kilonewton, and M is kilonewton and meter, right? It's a moment. But M is changing. It's like an equation, 6x. It means that if somebody put x equal to 0 at the beginning, M is 0. If he puts x equal to 3 meters, right, then M1 is another number, and so on. And for each x that you put, you substitute here, you're going to get a different number. If somebody is interested to know what's happening, let's say at this point of the beam over here, okay, and x here is 7 meter, sorry, not 7, because we start from the beginning. Let's say this section is 5 meter, then we say x is 9. So 9 belongs to the second section, like this equation here, and we use M2, and we can find M2. All right, that's simple. All right, but let's take another look at this equation. What is the relation between this M1 and V1? Take a close look at them. Like M1 is 6x, V1 is 6, right? This 6 here, this 6 here. What about M2? Like M2 is minus 4x plus 40, and V2 has like this minus 4 here, right? You see this equation? So do you think, is there any relation between them? Any idea if there is a relation between M and V? Do you think it's safe for me to say that V always is derivative of M? So V always is derivative of M. Look at these equations again. So if you take the derivative of M1, you get V1. If you take the derivative of M2, you get V2. So in general, we can prove that this is valid. Always V is derivative of M, and that's a good thing. In exam, in assignments, and whenever in future we solve a problem, we can quickly check to make sure that this relationship is valid and we haven't done any mistake, right? Here, like, if this is valid, then we are good to go. V always is derivative of M with respect to X. Okay, so let's move on to the next portion of this problem. Now in this example, the question is asking us to basically draw this V and M. Okay, it's something not related to a static, it's more like related to math. Let's do it quickly together. Again, I draw my boundary so I know where I am. So always try to draw these boundaries because then you avoid any mistakes. So our goal is to draw these V and M. Remember, it was our second objective, right? So this is V as a function of X, and this is M as a function of X. I'm just going to write down the equation that we found. So we found V1 equal to 6, V2 equal to -4, and we found M1 6x, M2 -4x plus 10. We just want to draw this graph of these V1 and V2, right? So V1 is easy. It's 6 and it is for section 1. So I just draw a line here. And let's say this is 6, okay? And V2 is just a constant number, -4. And I draw -4 here. Okay, this is then going down there, and it is -4. Okay, this is a graph of V. V is constant number from the beginning to this point 10, like at point B, and then it is -4. We just draw this graph, two constant lines, two horizontal lines. And our graph, to show like this discontinuity at the beginning, at this portion of this graph, always in math, remember, we connect this point to the x-axis to show that there is discontinuity here, like this line here, this one here, and this one. And it looks nicer also. So that's a graph of V. What about M? M, we look at M, and this is a line, right? And 6x, it's a first order polynomial, or it's just a line, 6x. And remember, when you want to draw a line, you need 2 points, okay? This 6x, and let's pick 2 points. You put x equal to 0, gives you m equal to 0, and you put x equal to 4, it gives you 24, the boundaries. Okay, so like at the beginning on this graph at the bottom here, it's 0, and then at point which x is equal to 4, it is 24. So it's over here, it is 24. All right, like this point here is 24. Okay, and then the second one, so don't forget this M2 is valid for x's between 4 and 10, right? So only in this section. So again, put the boundaries there. X equal to 4, it gives you how much gives you? So let's go back and see if we haven't done any mistake. Okay, let's move back. Here, guys, are we? Oh, it's 40, not 4. M2 is -4x plus 40. So this guy is 40. Okay, all right. Let's put x4, and 4 give me m equal to 24, and x equal to 10, right? Gives me m equal to 0. Like here 24, and here is 0. And we just connect these points because they are line. All right. So this one is 0, this one is 0. So this is our graph of V and M. And looking at this graph, now we can get to our third objective, which is finding the maximum. If somebody look at this graph and see the biggest number that they can see in this graph is 6. So V max is then 6 kilonewton. And looking at this graph, the maximum or the top, like on the top point on this graph is 24 kilonewton meter. And we know that where they happens, at point B, right? Right beneath these 10 kilonewton loads. Of course, this is a simple example. It's maybe obvious. We know if this beam is gonna break, where it's gonna break. But for more complicated loads, it is important to find out where this maximum happens. So far, is there any question? Again, there is silent. I take it as that you are good. Now, we have like more 3 minutes. Probably we can stay a couple of more minutes longer. So we are done with this portion. And then we go for a break. So please bear with me for another 5 minutes and then we'll be done. Before I move forward, I just want to see if you guys can see any patterns in these V and M graphs. Okay. By pattern, I mean if you can see anything that gives you a hint how these graphs should look like. And let me draw these forces that we found. This one was 6 kilonewton and this one was 4 kilonewton. Okay. Try to see if this V and these numbers give you any hint or anything. For now, we're just looking at this V, okay? And by pattern, I mean any hint that tells you that there is a relation, there is a correlation between these graphs and this number that you can see there is equal to dm dx. Then if we look at it like this one, dm is equal to v dx, probably if we integral, right, then it means m is integral of v dx, and integral always means area. So then we can guess m is always area of v graph. Okay, let's put all of these things together and see if we can find some nice patterns to help us drawing these graphs. Let's see. I have a 6 kilonewton here, okay? So you see there is a jump from 0 to 6 here. Then I don't have anything on the beam here, right? Nothing on the beam, and you see a constant line goes all the way down there. Now I'm at this point. I see here a 10 kilonewton point, and it is downward, right? It's going down. How much I dropped? So from 6, I dropped to -4. You see this drop here from this point to this point, it's -10. Right? This is -10. And this -10 is exactly the number that we see here. Right? And then what happens after that? There is nothing going on the beam. And as we can see, it's just a constant line going all the way down there until here. And then here on the beam, we have 4 kilonewton upward, right? You see there is a jump of 4 going all the way back there. So remember, we start from 0, we return back to 0 because it's equilibrium and everything has to back to number 0. And the second thing is this area that Aditi mentioned. So if we look at the area of this portion, what's the number? The area of this rectangular is 4 multiplied by 6, right? So the area here is 6 multiplied by 4, 24. What is this 24 on this M graph? We see this 24 here. All right. And then what is the area here? So from math, we learned that it is below graph. It must be negative. So if it is negative, then the area is minus. So this is 4, this is 6. 4 multiplied by 6 minus 24. So 24 minus 24 gives us 0. So at the end, we should expect 0. All right? So in other words, anywhere that we need to find M, we just need to find the area. For example, let's say somebody is asking us to find M at this point. Let's say at this point of the beam, okay? And tell you that this point, it's 1 meter. And you have only the V graph. All you need to do is just finding the area up to that point, okay? From the beginning area to that point, which is 6 multiplied by 1. Imagine that you don't have this M graph, okay? Always at any point when you want M, you just need to do find the area. Remember, above the graph, above the X is positive, below is negative. All right, so, and I need just 1 more minute and then we go for break. So with these things that we know now, okay, let's pretend that we don't know any equation for this problem. That's the same problem. Let's pretend we don't know any equation and we just want to see if we can draw the free body diagram, not the free body diagram. I'm so used to term free body diagrams, anytime that I want to say V and M diagram, I say free body diagram. So this is, we know, 6 and 4. Okay, so here what we want to do, okay, as the question is asking, we want to find out V and M graphs or diagrams without writing any equations. Already we did, but we pretend that we don't know the equations. Let's see if we can do that. If we can do that, it means our life is going to be easier, right? Oops. So we want to draw V and M. So this is V, X, M, X. Okay? So I'm just going to follow what we just learned for the graphs. So at the beginning, let's look at just V. At the beginning, I have 6 kilonewtons, so I have a jump of 6. I jump up 6 points. Then I don't have anything, so I stay where I am in a constant line. Then I have 10 kilonewton, so it means I have to jump down 10 units. So it means if I'm at 6, this has to be -4. And then nothing is going on. Everything is constant. I stay where I am, so constant line. And then I can see 4 going up. So I have to jump up 4. I return back to 0, so everything is good. Now I want to draw M. So if I want to draw M at the beginning, remember, at this point, beginning of the beam, moment is 0. At the end, moment is 0. MC is 0. MA is 0. Why they are 0? Because this one is a roller and this one is a joint. And a joint, remember a joint and roller, there is no bending moment, right? They can freely rotate. So at least I know for this M graph, the beginning and the end, they are 0. So if I know one point in the middle, then I'm good to go. Can we guess this point? Yeah, it's easy. We know that in order to find the M for this point, we need to just figure out the area up to that point. So I calculate area here, gives me 24, right? Area is give me 6 multiplied by 4, 24. So this point is 24. So V is a line, M is integral of, V is a constant, right? V is a constant number. M is integral of V. Integral of a constant from math, we know is going to be a line. So I just connect these lines together. So this is my V and M diagrams without actually knowing any formula. All right. So it's getting late, guys. Sorry, today took longer. We come back in at 10:30, and we solve another example for this one, so it becomes clear and you can understand it and easily solve a problem. All right. See you in 23 minutes. Bye for now.